hopefully everybody can hear me.
Yeah, we can hear you. You can start from now.
Yes, Mark.
I'd like to welcome you all to this tutorial come workshop on hybrid system simulation standards. This workshop grew out of some discussions and some ideas about a year or so ago, and is really aimed at addressing a level of simulation that a lot of us have looked at in different respects, but there seems to be some issues about getting it standardized and connecting things together. It's really, if you like, one way I like to think about it is the next level of simulation up. Martin later is going to give us some presentations from the Accelera standpoint, and I think he'll probably make it a little clearer what he thinks about this as well, which is good. We've got a lot of presentations to get through. So without further ado, I'm going to get going. The basic idea about this workshop was indeed to start a dialogue more than anything else. The thought here is that there's a lot of different simulation standards out there, and a lot of them are not overlapping or connected together. And what's required more than anything else is discussion. So that's really the key point about this workshop. Where we go after that is currently somewhat more open. So the workshop itself, the plan overall kind of was to do this workshop, and the first plan for doing the workshop was, 6 months ago or something in Toulouse. For obvious reasons, that didn't happen. And I think
Mark, a quick question. The right side of your window is blocked, probably by a chat window or so. The right side. I think there is 10% missing at the right.
I can't do anything about that. You can.
Well, this is better then.
I can possibly. If I do that, does it help?
Nothing. So you're not in presentation mode now. You're just sharing your editing window.
Okay, if I do this now, is that better?
No.
In which case, I will.
I guess it's better to continue in this mode.
Okay. So yeah, the original plan was to have a workshop in Toulouse. That obviously didn't happen. This is kind of effectively kind of second choice to do it this way, and it's going to be challenging for us all, and I think we all understand that, and I think we all understand why. Longer term, where do we go after this? Obviously, we want to get the discussion going. We want to foster the discussion. There is also the possibility to start working groups either within the auspices of the IRT or potentially within one of the standardization groups like Accelera. So that's obviously a possibility. But at this point, the key activity is to get the discussion going. So one of the things that I wanted to bring up here was what do we actually mean by this this terminology, the hybrid and so on and so forth. There are people who have used the word twins, cyber physical. There are so many different words for this. At this point, in terms of what we're discussing here, I don't think we should exclude any of those. I don't think we should exclude any particular domain of simulation. The real concept, as far as I'm concerned, is how we enable simulations of simulations, or the next level up, as I like to call it, to connect together. So a couple of questions about, well, why would we do this? I think it's widely, I mean, I suspect I'm preaching to the converted. Simulation is becoming increasingly important. But increasingly, the thing that's more difficult is no longer the system on chip or whatever it used to be. It's now much more at the level of multiple systems or complex systems together. And it's at that level that, that we're really addressing things. So, I mean, this has been the case in the aerospace industry for decades already. So they already have a lot of answers to some of these questions. From the point of view of you know, the mobile arena from which a lot of System C, for instance, comes originally. That's been less of an issue up till recently. It's now becoming much more of an issue. So I would suggest that there are some things that we could learn at that point. So why existing standards? Well, the thing is, we are all in our standards bubbles. And some of the standards tend to be industry or domain specific. Some of them tend to have wider reaching ambitions, but maybe potentially only used by certain industries. There's a degree to which the standards bodies and the standards themselves are the right place for this activity to happen, but very often those standards aren't known about from one industry to another. So the challenge here, as far as I'm concerned, is to join the dots up, if you like, and to find out where the activity should best happen. So a couple of questions before we get into some of the discussions. What simulations are you currently using? What systems have you currently got? What subsystems have you currently got? For instance, are there devices and models and things available in different standards that you can't currently use because they're outside of your the standards that you currently use? So I was at a workshop some weeks ago where there was a big debate about the availability of a particular model of a particular device. Well, that device, as far as I was concerned, was available, but it was not available in the standard that was being discussed. So yeah, what's missing from the existing standards and where can we better align? So I don't want to go too much more because I suspect that this topic it's the topic of today's workshop. I suspect each speaker is going to speak to it. So a little bit of information about how we propose running this workshop. I suspect each speaker will do something slightly different, but the plan is that each speaker is going to speak for a relatively short period of time, 10-15 minutes or so. We have 5 speakers in total. We have a 2-hour period between now and midday. We are between ourselves and lunch. The idea is to keep each of the discussions the presentations relatively short. I hope that you've all had a chance to look at some of the information that has been already sent out. And then hopefully we'll open it up a little bit more to discussion. So by all means, chip in all the way through. I think the Zoom call is such that everybody has the ability to stick their hand up and say something. By the looks of it, we're about 50 on the call, which is great, but in a way we are only 50. So by all means, put your hand up and say something. If you're confused about something, if you've got a point to make, I think it would be good. Somebody's got it working. That's good. Right. So in terms of the running order, the first one up is going to be Martin, who's going to speak around the Accelera standards. We'll then have Rashid talking about SMP and SMP2. Jean and Oliver are going to talk about VHTNG from aerospace. Jean-Marie is going to talk about FMI and FMU, and Andreas is going to talk about OpenADX. If you don't know these people, each one of them, as far as I'm aware, is really the kingpin in their particular domain. So they are extreme. We're very, very lucky to have these people talking to us about these different standards. They're the right people, and it's good to have everybody involved to try and work out where there is overlap between these standards. So without further ado, I'm going to pass over to Martin, if I may. Martin, go for it.
Yes, can you unshare, because it says that I cannot share my screen while others are.
There you go.
Visible? Yes, it is.
Good.
Full screen?
That's fine.
Full screen
Okay.
works.
Yeah, it's full screen.
Okay. Thanks for the introduction, Mark. Welcome everyone in this hybrid system simulation standardization workshop at DVCon Europe. My name is Martin Barnesconi. I'm the Accelera Technical Committee Chair. So besides my normal job in NXP, where I am in the design methodology department, driving design and verification standards, especially at the system level. I also spent quite some time in the international context of EDA standardization within Accelera and IEEE. So I just pick a few topics which are relevant for this discussion today. First, a quick overview on what the Accelera System Initiative is all about. I give an overview of the different standards, but since we said we keep it short for the intro, I only zoom in on 2 of the 20 plus standards Accelera has developed over the last decades. So I will zoom in on the System C standard, a bit of history, the ecosystem which has been developed and the different use models and associated abstraction levels, and relevant for, I would say, reuse, integration and automation is another standard we develop in Accelera, which is called IP-Exact. And I will zoom in on the flows and the capabilities of those standards, because I think they are also applicable beyond semiconductor design, because like Mark says, the main focus of Accelera is design automation standards, primarily in the semiconductor domain. So to give you a high-level view on what the mission of Accelera Systems Initiative is basically a standardization body which offers a discussion platform, standardization platform, where different industries will come together. I will have a slide on the members as well, where we basically collaborate in an open manner to develop standards, and with the aim to bring them eventually to IEEE. The primary focus is on design and verification standards for electronic products, and the history or the background is obviously integrated circuits, but you see that as SOCs are getting more complex, they need to be integrated into a bigger systems. So we are gradually moving from semiconductor to SOC to system level type of methodologies. I already mentioned the membership. We have more than 40 members currently, corporate members, associate members, and also we have a membership for startups and universities. So all those companies are active in one of the working groups, which I will touch in a minute. So you see that based on the company logos here, you get a bit of an idea on which industries are making use of Accelera standards. That is depicted in this slide, which standard activities we have, divided in different working groups. This chart shows partitioning in 3 segments. Obviously, it is not that strict, and some standards are even addressing the design and verification space or integration space. But at a high level, we can say we work on more design, system design and design integration related standards for analog and digital. And you can think about System C with all its extensions like transaction level modeling, configuration, control, synthesis, System C AMS extensions, but also System Verilog, the design aspects, and System Verilog AMS standardization is part of that bucket. Then we have at the right side the verification space, where we have also for analog and digital, which covers the universal verification methodology. Recently, new working group has been established on looking at AMS extensions, but we also have portable stimulus, multi-language, unified coverage database, and the open verification library as working groups or standards. And the last item at the bottom of the slide, standards related to what we call integration and infrastructure. IP security assurance team, which is looking into design methods and defining attributes to be sure that your IP is compliant to a certain security rules. We have a functional safety working group looking into the functional safety methodology, data model associated to it. IPXect, as I mentioned before, scheme, IP tagging, OCP, and system RDL for register definition modeling. So more than 13 working groups are currently active. Some items listed here have been developed in the past, and the standard is available, but there is no active development. And for this workshop, I only zoom in 2 areas. Of course, if there are more questions, we can discuss that later if you want to address other standards, but I primarily zoom in today on the System C part and on the IPXect part. So the System C ecosystem, as I already mentioned, it contains a core language depicted here in the right picture in blue. And the core language contains many elements to create system level models. And a few years ago, also the transaction level modeling, which was a separate extension, has been part of the core language. So you see that part also in blue, but there are many other extensions available, like the mixed signal extensions, System C verification library, and a library for configuration control and inspection. And there is, I think it's not depicted, a synthesizable subset defined to support a path from a behavioral model into via high-level synthesis into an RTL description. So we see that System C is widely used in various areas. It's at the end a C++ based language. It is in that sense not really a language. You can say probably is more a dialect or so, but it defines a set of classes, methods, and an API which enables system level modeling. Both at signal level as well as transaction level. I will come to that in a minute. Facilitating architectural exploration and performance modeling, more abstract modeling approaches. As already mentioned, AMS and high-level synthesis flows can be supported at the system level. And especially System C is very suitable to create virtual prototypes which enable the creation of, or which help in the software development. And you now also see that from the semiconductor domain into the tier 1 domain or even OEM domain, those virtual prototypes are really of use. System C is available as IEEE standard under the IEEE 1666. The current version is 2011. There is a working group currently active in IEEE updating that, which is probably expected in the years to come. And there is also the AMS extensions, which is the 1666.1 standard, which was released in 2016. What is interesting to mention on the System C ecosystem is that it actually contains 3 angles. There is the community part, which is the users, not only in companies, but also the open source users. And we interact with those communities via GitHub and via forums. And as we have seen in the keynote speech from Moshi, is that open source is recognized, but you need to have a few prerequisites in place that it really gets a sustainable ecosystem. And I think that is what is depicted in the other angles here in this triangle, is that it is based on a IEEE standard, which makes it a very solid reference. So the IEEE standard basically defines the language reference manual for System C, which is the API. And then any company who like to support System C can follow the language rules to support either tooling compatible with System C or even a simulator compatible with the System C standard. And the role of Accelera in this, which is depicted here in the bottom right, is that Accelera has been at the start the initiator of the System C standardization, but we also within Accelera develop a lot of other materials material like reference implementations and the actual simulator, but also user guide, utilities, examples to really make the standard of use that you can actually integrate it in your design flow, because only a standards manual as a paper book is not sufficient. You need to make it much more tangible by offering some additional material like reference implementations and examples that the community can get really hands-on. A few words on the abstraction level, because at the end, use cases are very often connected to, okay, at which abstraction level do you want to model and what is included in the model or what is not included in the model, and what is then the most suitable languages. So here I have a high level view on the different abstraction levels and what does it mean for the abstraction and the type of description you capture. So signal level is in the semiconductor domain more or less the lowest level available, cycle accurate behavior, even down to gate level. Obviously, System C is not meant for that, but if you want to do cycle accurate behavior, you can do that in the System C domain. And it's the first level of abstraction, abstracting away the gates, and even some basic of low level timing is, and like delays is excluded. Preferably we skip signal level, because the more cycles we have, the slower it gets. So we tend to focus on the transaction level, and there we have the TLM standard, which defines different modeling paradigms to deal with this notion of time. So there is the loosely timed mechanism, formerly known as a programmer's view. So there you try to really abstract away your time. You want to move into more functional calls only. But obviously, if you want to have some notion of timing, either cycles or events, you could implement that in TLM as well, using approximately timed or even cycle approximate timing schemes. And depending on the use case, we need to agree, okay, what is the most suitable abstraction level and what is the associated timing at that level. And then the upper level is algorithmic level. This is a bit outside scope of System C, although System C is C++, so you can even do untimed modeling if you like. But we also see that there are other languages out there which can be used. So the main focus is transaction level, connecting it to the signal level, where System C has quite some nice features defined. In view of time, let me quickly say a few words on the IPXX standard, which is also an IEEE standard 1685. It is an XML schema, which basically is a sort of container format to define an electronic data sheet. And as part of this electronic data sheet, we have the items listed here, which are defining that data sheet. So interfaces, components, abstractions, when it is dealing with different interface abstractions. You can compose a design, you can configure it, and there is an automation flow available using a tightly coupled interface for flow automation. A few words on how that ecosystem looks like with the different flows. Here in the top of the picture, you see that an IPXX flow supports multiple users and use cases. So an IC architect, system architect can use it to compose its system architecture description, but that can be refined to such a level that it is also suitable for the IC integrator, because of course we always want to match the IC architecture, the system architecture with the IC implementation. But obviously the verification engineer, which is at some point in time getting hold of the design under test, he wants to verify it, he wants to create a test bench around this, and also IPXX offers ways to automate parts of the test bench generation, for example, the creation of the UVM reference model. A software developer requires views. There is a hardware abstraction layer. He needs to have drivers. Also, IPXX can help to generate the software headers. And last but not least, there is always a documentation part of the flow. So how do you create your data sheet or user manual or other documentation? And preferably that is always consistent with the with the implementation, being it an IC implementation or an architecture definition. So if you can connect your IPXACT flow to the documentation flow, you really make the flow very consistent. At the left side, you see different IP providers which offer IP in IPXACT descriptions, which facilitate integration in an easy manner. And at the right side, you see, in line with the use cases I described, you could go into different tools for documentation, obviously, flow towards the data XML language can be done. If you want to integrate processors, you want to integrate with the ARM ecosystem, that is feasible. And there are different simulator platforms available, or UVM verification methodology you want to connect to. And with the automation capabilities of IPXACT, you can support those flows as a consistent, in a consistent framework. I think I mentioned all those items already on the previous slides on the different flows and capabilities. So in view of time, I skip it for now and we can come back to it at a later stage. So to wrap up, Accelera system initiatives focusing on EDA standardization, more than 40 members active in working groups, developing the standard, but also additional material, supplemental material like reference implementation to make it really hands-on. The System C standardization itself has a history of more than 2 decades. I skipped some slides, but you can look in the backup. There is more than 20 years history, and we still evolve the standard, especially towards system level or moving into systems of systems. And the abstraction methods should be reviewed and see if they are suitable or whether we need additional additions to that. And when it comes to flow automation and reuse, IPXACT is a true enabler. It's a metadata definition which enables you to capture your design intent at the architectural level or at the implementation level. And you can create any flow and make it even EDA vendor neutral. I think that concludes my talk. I included here some references for you that you can study material later. If you have any questions, we can discuss that later in the workshop today. Otherwise, you can contact me offline.
Thank you very much, Martin. Are there any questions to start with? God, stunned silence. Martin, I'll kick off just quickly. I mean, we need to move on because time is going to catch up with us and run away with us. But just very quickly, it seems to me that we have kind of four C's that we need to be thinking about when we connect at the next level up, if you will. There's the connection itself, the mechanism by which we do it. There's the mechanism by which we describe what needs to be connected, which I think in Accelera terms relies heavily on IPXACT. There's the configuration of the objects that we want to connect. And finally, there's the way in which those things connected are going to be controlled. At this point in time, would you agree with me to say that, for instance, System C, as it stands, kind of has this basic assumption that everything is going to be written within the same System C environment? And at the moment, we don't have a means by which we can say how System C would exist, or a System C model would exist within a wider context.
Yeah, a fair point. I think most of the extensions which have been developed over the years are, like I showed on my slide, are built on basically C++ System C language. And that makes it an ecosystem which is very coherent and basically all under one roof. But you bring up a good point. If there are initiatives in other domains, then you also need to think about, well, let's call it co-simulation interfaces. And how do you get data back and forth, not only from another simulator into the System C domain, but also even between different System C kernels which run independently because they describe a system at a higher level.
I think, at least to my mind, that's kind of the big challenge that we face and we go through today.
Yes, the other thing is that I think we also have some unique elements related to that. We within Accelera with System C, we have defined all with the standard along with the proof of concept. We do have also a simulator, and you see that many other initiatives, they do not have a simulator as a sort of standard or API definition. So they have been focusing more on interfaces, because the simulator is then something they buy or they get out of a partnership with other vendors which do offer this type of simulator. And I think we do have, I mean, we as open source community or Accelera, we develop actively the open source reference implementation. So focusing on interfaces would be good, especially if you cross the boundary from one simulation domain to the other simulation domain. But it would be worthwhile looking into whether the simulation engine we have and the abstraction methods we have, whether these are also applicable in other domains. So think beyond the interface.
Yeah. Okay. Hopefully there'll be time at the end of this workshop to keep discussing and come back to some of these issues. Let's move swiftly on then. The next speaker is going to be Rashid, I hope, if he's there. And he's going to talk to us about SMP, which shares many of the same letters as TLM, you know, in a kind of strange way, because it's also called SMP2 and TLM is TLM2. And for those of us who know a little bit about one or the other, I think you'll find that there's an awful lot of overlap. So Rashid, I let you present.
Okay, thank you, Mark. I suppose that you are looking at my slides now.
Yep, looking good.
Okay, perfect. So just to present quickly myself, so I'm Rashid Tataouri, working for Spacebell now since a couple of years, since 1994, in the space domain. So we are mainly active in the space activities, and one of these activities is related to modeling and simulation. That's a domain in which I'm working now since 20 years. And also in there, I'm active in the standardization group in order to try to see how we can rationalize the modeling facilities between the different stakeholders. So let's go quickly to the presentation. It's a presentation done by Spacebell and myself and Airbus, which from William Maroui. Unfortunately, he was not able to attend today. Okay, let's, so next slide. So the SMP stands for the Simulation Modeling Platform, which is part of the ECSS. So ECSS is the European Cooperation for Space Standardization. It was formerly known as SMP2 up to now, and the new standard is now called SMP. So it's going the other way around. So the first version was SMP2, and the following standard is SMP. However, SMP, it's more an evolution of the SMP2 standard, and it's not a revolution of each. So we have to see that establishing such a process takes time. So we started the SMP discussion around 2005, and finally we just accomplished the first standard version SMP quite recently. It was by the end of 2019. So the content of the standard, it's a specification of the standard, of course. The related C++ header files, we will see that it is the main target language that is used by the SMP. Either we can try to identify other languages, but today C++ is the target one. And of course, we use data modeling definition based on XSD files, which are XML files, in order to define all the artifacts needed by the standard. So who use the standard? So the standard it's quite widely used in Europe and in the space domain. So I'm not aware of another usage of the SMP. It may, but from what I know, its main usage is in the space domain within Europe. And the space domain, so it can encapsulate rovers, it can encapsulate launchers, satellites, any activities that needs to be modeled or simulated within the space activities. So where do we use these simulation facilities? It's we used for what we call the SVF. It's the facilities that are used to test the onboard software. That's quite an important aspect for the testing. We use it for the system testing also. System testing at any level. It can go from an equipment level up to the satellite or the constellation level. We can use it for the hardware in the loop facilities, which include real equipments in the loop, or for the EGSE, it's acronym for electrical ground support equipment, in order to test real equipment. And of course, we also use it for operational and training simulator in order to verify the procedures to be applied on the real satellite. So we do it better in simulation before we do it in real life. What is covered by SMP? So SMP, it's based on interfaces. Implementation is left to the developer choice, and these interfaces are related to how a model shall use the simulation infrastructure. So we have interfaces to define strictly these interactions. We have interfaces to define how models are presented. And also interfaces on how we can connect models to each other. And of course, there is a state machine that will allow to correctly synchronize the activities between all the models that are involved in a simulation. So the simulator interface allow managing models through factories. So the main services are the time, we will say that in details a bit later, but they are related to time management. They are related to the scheduling also, how this is the dynamic behavior of the system. That's mainly the dynamic behavior of the system. And of course, we have the usual logbook that is still needed because we don't have yet the mind reading. So the logbook it's still needed, and it's very important. And also one very important point is the publication. So we have to know that models shall or should publish any relevant information that may be useful for either interacting with the other models or interacting with the user. So this is a state machine that each model shall, the simulator shall follow, excuse me. And just to summarize this state machine, we don't need to go in details now. We have mainly the setup phase for building and configuring the simulator. We then have the execution phase where basically we run and hold the simulator in order to make the time evolving. And of course, we also must have the possibility to save and restore context. This is very important because it allows us to to avoid restarting a simulation from the beginning and save time and start from a saved context during a simulation. So, of course, models can be organized. It means that models can contain other models. This is just a composition mechanism, in fact. And also, any model can, of course, be instantiated as many times as needed. For instance, a model of a GPS, of course, we can instantiate it 2 or 3 times. It depends on the number of the same equipments we have on board. And of course, we have to configure it specifically in order to provide the specific data related to each GPS. Each model will own some basic information, which are the fields, the events in the interfaces. We will have a look to it right now. So for the communication, this is ensured by the fields that are made available to other models. So sorry about that. So the fields that are variables that are made available to other models, they can take care about the field value whenever it's needed by this other model. Events, they are used for notifying the other potential connected models that something is happening. It's a dynamic notification to the connected models if they are. And we have finally also the interfaces, which are I would say a more complex or sophisticated notification that allows multiple flows with connected models. So within the interfaces, we can make a more complex iteration or exchange with the connected models. While with the events I just mentioned before, it's just a simple notification. It's just like a signal telling to the other, okay, this is happening. So we have also what we call the operation in general. So one important point is that the models can be scheduled either externally, so we can from the integration point of view define, okay, this model can be scheduled every 10 nanoseconds, 10 milliseconds or whatever, or the model can schedule itself also. So, for example, if a model is powered on, it can schedule something that will happen after, I would say, 30 milliseconds for modeling a warm-up period, for example. So this is a dynamic scheduling, which is quite important for the modeling we have in our activities. We can, of course, have defined operations that are dedicated to users. Usually, these operations are not used by the other models, and these operations are usually used by the user in order to inject faults or to trigger some specific behavior on a model. Okay, and we have, in fact, here in the SMP modeling two levels of modeling. The first one defines strictly a modeling, the model interfaces, how it defines how a model does look like, and it is defined in a standalone manner. So we can say, okay, basically this is my model, these are its interfaces, and this is the kind of behavior I'm having on my model. And the second level define how we can instantiate and organize these model instances. Usually this is done by the integrator, and which will assemble these model instances together and connect them to each other. For this definition, we have an XSD file, an XML file that defines exactly how a model, the interfaces of a model. And also we have another schema, another XML files that will define how these instance models are instantiated and connected to each other. So there are two different set of artifacts. We have other kind of artifacts, but are less important, and I will try to stick to the essential artifacts here. So we have also artifacts that are related to the scheduling and the configuration. And as I said, this is less important, and we can come back to it later if we have more time for our slot. This is an example that shows, for example, what we have in a catalog. We have, for example, the defined interfaces and the defined models that are involved in my simulation. And for each model, we have the subset of models that can be included and the interfaces that are also implemented. That's on the left side. We have then the definition of the models we have that are included in a catalog, which is an XML file. And on the right side, you have the assembly. It's another XML file that defines how we do instantiate these models and how we do connect them to each other. So for the XML model creation, so it's we have they are defined using UID schema, and we are also using factories in order to be able to instantiate a given model. I think we are it's maybe too much details here, and we can come back to it later if we have more time. So don't hesitate later to come back to it. And also now, if you can address what is related to the process and the model exchange, we will try to address the development process and how we can have generated or imported models from other sources of modeling. Usually what we have in our process, it's activities related to the design, the development, and after that we have the integration and scheduling phases followed by the execution. And for the design phase, what we have is a design facility which is based on the UML modeling. So we have a use of an UML editor, whatever the editor, the best editor you can have, you can choose it, which can model any model in your system and generate the related catalogs, which defines how your models do looks like. So this catalog is generated, and of course we can still have a catalog editor, and we still have a catalog validator in order to completely validate the catalog against the XML schema. During the development, we have a code generator that will completely generate the wrapper code based on the catalog, and in which we can also add the package editor. A package is just an assembly of the models we have in one or multiple catalogs. And finally, we can include our own behavior code and compile it and make it and have binary library that can be used later. And during the integration in the schedule phase, we have to make an assembly. We can do it using an assembly editor, so where we can instantiate our models and connect them to each other. We have also a schedule editor whenever needed. Otherwise, we can have the models scheduling themselves, or we can also have an external schedule telling, okay, in any case, I want this and these models to be scheduled every for example, every 10 milliseconds. And also we can ask the system, okay, these models I want to be scheduled 3 times from that time for and every 50 milliseconds, for example. And at the end, we have an execution where we can configure the models we have using a configuration files, and we can execute finally the complete simulator based on the assembly, the library of the models, and the configuration files we have defined.
Rashid, just to warn you, we are seriously running out of time. So if you could move quickly.
I'll try to. So this this slide just to show that, of course, we can generate SMP models from external sources. Today, the main external source we have is the MATLAB Simulink importer using the Mosaic tool from DNLR. And at the end, so we have a simulation infrastructure that can execute models using the dynamic libraries and the assembly and the schedule files to run the simulation. What is also important is that we have a reference architecture that is defined next to the SMP modeling that will allow us to better exchange the models. In fact, what we have tried to do is to define how we can model an equipment and how we can model the system interfaces and the external interfaces of an equipment. This is really, this is mainly oriented for the space equipments, but I think that this may be useful for any kind of equipment. So this is defined on top of SMP, and with CNES, Airbus, and Thales Alenia Space, we have defined an initiative for space innovation and standard, where based on the reference architecture, we have defined standard interfaces for exchanging equipment models based on standard interfaces. For example, we have standard interfaces for the CAN, for the 1553, for the space wire, for the one wire, or whatever interface that can be used in any of our space equipment. This is something that is based on top the SMP2 modeling we have defined. That's it, and I think that the next slide we can skip it. It's just to show that our approach is strongly component-based. It's a component-based approach that is used. Okay, that's it. I will stop here and let the floor to other, unless you have any question related to this presentation.
Are there any quick questions? Otherwise, I suggest that we go on. One of the issues that I didn't think you touched on enough, and I think is very interesting with SMP, is the way in which time is dealt with. But maybe it's something for later on. Are there any other questions from the audience? Otherwise, we'll move quickly on to Jean and Olivier. I don't know which one of you to speak first.
Yeah, I will. This is Jean. Olivier is next to me, and we will start.
Okay.
So, hello, everyone. Hello, everyone.
We're not seeing your slides yet.
Yes, I'm trying
Share
to
screen.
share screen. Yes.
C'est bon.
Perfect.
C'est mieux là? C'est bon?
Ouais, c'est parfait.
All right. Okay, so good morning. My name is Jean Castores. I work for Airbus in the facility of Toulouse for the simulation department, who is in charge of making engineering simulators that are used to simulate the aircraft components, mainly the embedded computers.
Hello everyone, my name is Olivier Fourcade. I'm working with Jean in the same department, and I'm more in the simulation of simulation benches of test benches, and I will present you later the standard we are working on for this specific case.
So our focus would be the simulation of aircraft system. But prior to working for Airbus, I worked in the design center of Motorola Toulouse that became NXP after. And so that's why we came to cross virtualization of components that we are trying to reuse. And that's why I'm in contact with Mark for reusing the virtualization capabilities into the aircraft simulator so that we are more truthful to the software that is used on board the aircraft. Okay, so we will get into those details. So the project name is VHTNG and Test Automation. This is a research project. VHTNG stands for Virtual Hybrid Test Next Generation, and TA for Test Automation. Hybrid means you have at the same time a virtual representation of your embedded computer on the bench, or you can connect the real physical computer on the bench when it comes from your supplier. So we'll go through the project objective, the research project objective, the architecture of the future proposal that we have, some use case that we are conducting in order to validate with our partners all the standard that we propose, the open standard that is now available, and that Olivier will definitely insist on that, and a short conclusion. So the project is dealing with company both in Germany and in France, and is dealing with multiple Airbus BUs. So we have 9 companies on the French side and 9 companies on the German side. It's a cooperation between 2 states, France and Germany. So the funding money is coming from the 2 states that actually originally was not a European project, but the two countries agrees to come and see the demonstrator together in France or in Hamburg or in Toulouse alternatively. So that's a good cooperation example. So we have academics partners, BIBA and TUH. We have avionics equipment manufacturer, so they make embedded computer for the aircraft. We have people that are making the benches to test those computers. And then we have the integrator, so mainly it's Airbus, but business unit in France, Filton and Hamburg with Airbus Defense and Space and Airbus Civil Aircraft, okay? And also we are trying to extend our working groups to automotive partners such as Audi and Volkswagen. This is to propose bench open standards for those 4 markets, so namely satellites, because we are trying to work with Airbus Defense and Space, Manching, and also have discussion with Toulouse, cars, flight simulation, and aircraft. So the architecture, we try to solve a problem for coming from the design office where you can have an MBSE flow, which eventually is based on tools that you may have heard of. OSAM, probably not, because it's an internal Airbus simulator, but 3DX from Dassault, maybe you heard of. Then we propose our standard architecture that I will detail, which is trying to focus on the configuration of the bench, the performance of the bench, and the reuse of tests, which here is listed as command and service dictionary. We are working with partners which are making our equipment, and we try to drive the development of the equipment. For the manufacturing of SoC is just like if you were receiving a UART or a DPAA component from a third-party provider that you would integrate on your SoC. It's kind of the same parallel. Okay, and so we are trying to specify the equipment we get, and to set up rendezvous points for testing with this partner using the same bench platform, so the same test platform. And then we go to the acceptance. At this point is the acceptance into what we call the lab, which is the IV for flight test department. And those people put together all the computers and see if they work together to accomplish the aircraft function. And then we go back to our design office because we would like to use more and more virtual bench test so that we offload a little the physical test bench, such as the aircraft zero. The aircraft zero is an airplane in a hangar with all the complex system of the aircraft, so hydraulic, electrics, and computers. And that's the ultimate simulator. At this point, we go from a complete virtual simulation to a complete real simulation. The only thing that's simulated into the aircraft zero is the flight loop. All the computers are real at this point. All the actuators are real because this is where we are testing the aircraft just before the first flight. Okay. So in order to validate the standards we are trying to put on the bench, we have set up use cases with Airbus entities, with Collins, Safran, Deal, and LibAir, which each of them is working on a specific equipment of the aircraft. As you can see, the A350 communication for the Collins cooperation. The EIU is a computer between the engine and the main cockpit in the A320 with Safran. The oxygen and overall architecture of the bench with Deal in Germany and Hamburg, and also an air system with LibAir here in Toulouse. We actually use those use case onto a reference implementation. So it's just as Olivier will present to you, it's using a standard pushed into the reference implementation. It's made available to all the research partner so that they can use it and integrate their use case in their own company, but then they come to Airbus when it's integrated together in a multi-system environment. Okay, so I'll let now Olivier present the test automation part and the Vistas part.
Okay, so first with the continuous integration, you will understand why we need something dedicated to test. As mentioned, Jean, our panel of benches is very large, and when we go through the cycle of development, you can see that we face some requirements which are very wide, and we don't have today a solution to sustain all the phases of this continuous integration cycle. So this is why VHTNG, the VHTNG project and the test automation project are here. It's to support this will to get scalable and sustainable architecture to follow all the steps of the continuous integration cycle today. Okay, so regarding this slide, where VHTNG and test automation can provide answer today, everywhere you need a virtual bench or virtual platform to support a test or to conduct a validation. Of course, VHTNG will propose an architecture that could be used through the whole cycle. And exactly the same for test automation. The test you are defining somewhere in the cycle of development could be reused somewhere else later on in the development cycle. So this is what you see here. I'm not going to go into detail. I won't go into details regarding the name, but we have several kinds of benches, and in the aircraft industry, we face today a global problem, which is that which corresponds to the fact that we are beginning the design with something fully virtual, and the more in detail we go into the development cycle, the more into we are integrating real components, and so we don't have a platform a platform that may support this integration, this hybrid integration through the whole cycle. And of course, we don't have a platform and a test definition for which you can reuse what you define in the design then into the validation phase. And this is where test automation and the VHTNG project are giving answers. So from the design to the very end of the cycle of development. Okay, more than that, what's interesting with the test automation project is that we will reuse. The test automation project aims at reusing test scenarios and to enrich the base of tests so that you can have more detailed tests later on in the cycle of development. This is what we call observers and then adaptive testing. And we are thinking of a way to optimize that directly through very new technologies such as AA and things like that.
Okay, yeah, to complement what on this slide Olivier was saying, adaptive testing is really the capability using IA or other techniques, okay, to change the flow of your test during the test based on the previous results, but at a functional level. Because, for example, the test coverage in avionics system is not as easy as in microelectronics to compute sometimes. Okay, then this is the architecture we are proposing. It's a proposal. So it basically has three main colors. The orange are the function of the bench, okay, and the services the bench is providing. The dark blue one is the virtual ED247 standardized bus, which is connecting components which are modeling the behavior of an embedded computer. So Olivier will come back on this in further details. And then the light blue bus is actually the physical wires, so the real wires, just like they will be on the aircraft. At the beginning, at the center of this picture, you have a gateway function, but think of it as a function. This function can be centralized, just like on this figure, or it can be distributed into the virtual models of the bench. We are trying to create two ecosystems, one for the bench providers and one of the equipment providers, as shown on this picture. As you can see, and it's also the partners list I presented earlier. We would like to define this continuous standard architecture because we want to be able to change and play with Legos for the different function in the ecosystem of the bench provider, and also in the ecosystem of the equipment provider. As you know, on the aircraft, you have Honeywell, Thales, Collins, who are making different computers for us because it's part of the diversity that we want to maintain to achieve a higher level of safety. Because the fact of having different equipment manufacturer and not giving everything to just one is a proof of robustness for us. Okay. Then the idea is to have a standard for the instrumentation network bus. So we are using state chart XML for the test, a DDS-based bus here for the exchange of data between the orange boxes, and XML RPC schema for command and control in the first proposal. And for the virtualization of the avionics signals, we are using ED247, which Olivier will explain, which is standardized at the EuroCAE level and is allowing us to transport over UDP frame on Ethernet all the avionics signal we need. And then we want to be able to replace a virtual representation of the embedded computer with the real computer when finally they come from the equipment manufacturer. So the equipment, sorry, I went too fast. The equipment manufacturer, they are the Deal, Rockwell, Zodiac. Then you have the various companies which are providing the Legos for the bench, such as Nexias, Ferrat, Texat, and DSpace, for example. Okay. And then you have also a company providing the IOs, because those IO cards are doing the real connection to the physical computer when it comes. And ultimately, what we're trying to achieve with the virtualization of the computer is that the binary of the virtual component equipment is the same as the binary that will run on the real computer. This is important because for an aircraft, we are trying to build what we call standard, which is a set of software which is allowed to fly. Okay. Then we have the capacity and the definition of the virtual and hybrid, which is the capability to switch from the virtual component to the hybrid one, because sometimes it's we use the models, the virtual models, as environment models for other kind of simulation. But that's maybe detailed. We also have the ability to distribute between different sites, because we have benches here and there with Airbus. For example, fuel and landing gears in Filton, we have the cabin in Hamburg, and the overall simulation of aircraft 0 in Toulouse. And then we want to connect to test automation, and this is the connection Olivier already showed you, where this architecture must run the test automation scheme at any point in the continuous development of the equipment, which again, for that equipment concept is a physical concept for the aircraft industry, but for the microelectronics industry, it can be a block of a SOC which is achieving a function like, for example, encryption or compression of packets or etc. Okay, so this is really the parallel we could draw. Then a short slide on test automation, again, to emphasize the fact that we want to reuse tests throughout the development cycle. And a study was made that shows that if we have a manual procedure for a system under test written by hand and passed by hand, the time it takes to run the procedure is a little long. But you only invest in developing an automatic procedure if you run that test at least 3 times in order to shorten the test runtime and to automate it. If you run that procedure only 1 or 2 times, it's not worth the effort. But if it's more, then it's worth the effort, and you can share it through the V cycle. Then test automation is focusing on reusing MBSE model to do MBT. It can also do textual and scripting and natural language interface to generate the test automatically, and recording replay. This is more oriented for the aircraft, I assume, since this part is not really automated as far as too much automated as of today.
Jean, sorry, it's my fault. More than anything, we're kind of more than run out of time already.
Okay.
Could we skip down to the last couple of slides? I think you talk about VHTNG, the open source, and the conclusion, because we are really hard up against time. I know that means time involved, but
okay, just a flyover. So here I was trying to explain the different use case, who is doing what. Then we have to give you a feel of what a function is for us, is the remote braking control unit here with the virtualization of the computer that GreenSock did. Then we have the oxygen bench in Hamburg, which is doing control of the oxygen systems in the aircraft, the configuration of the bench, the part and the view of test automation here. So I will leave it now maybe to the the cabin use case also in Hamburg, to give you an example. I give it back to Olivier, which will explain actually what is one of the most in all those standard efforts that we did. The most advanced one is the Vistas or ED247 group, and Olivier will present that to you now.
I will go very fast. It's just to remind you that we have to develop technology that sustain the whole V cycle. So what we did with in the ED247 standard is that we made a communication model to sustain the virtualization of all the avionics, the usual avionics protocol we can face in the aeronautical industry. So somewhere it looks like what SMP is proposing. It's just that it's really bound to linked to those avionics protocols. We made a communication model. I won't detail here. If you have any question, don't hesitate to go there. There's a kind of short process proposed, which looks like really what I've just seen in SMP. So you can have parallels with that. And we propose an open source distribution for this standard today. It's available, and you will see that it will be proposed by Jean at the end of those slides. And what the link?
Yeah, but insist more on ECD, ECIC, maybe.
Yes, just one of the main concept to understand is that a component, whatever it is, virtual or real, we don't care, but a component which is something that you will integrate in a bench is known in two states. The first one is just it's just this is inputs and outputs. It's a declaration of its capabilities to exchange data. It is called the ECD, the EC for EuroK 247 component description. That's the ECD. And then you have to implement really this component into your bench. So it's the instantiation of that. It's the ECEC. It's the bench architect who is able to know what kind of resource it will attribute to this component. And once the ECEC is done, the EC, the component itself, shall be able to configure itself according to the ECEC. Thank you very much. That's what you have to understand. It corresponds more or less to all the XML files I've seen in SMD, but I don't want to go to be too short or to not details enough on that. But I think there are links between those two standards. The link with VHTNG. Okay, it's just to make you understanding that this standard is the backbone for the VHTNG architecture for any part, for any any application, any avionics application or any avionics bench that will use either a virtual component or virtual and real component, which is what we are calling hybrid bench. On top of that, we need today to define through VHTNG, or VHTNG needs to define, of course, some parts that are missing in the ED247 actual version, which corresponds to command control, monitoring, and direct configuration. And those parts are going to be standardized through the ED247, or the working group working on ED247 with completely or closely with the VHTNG project. In other words, the VHTNG project, the VHTNG needs will go directly into this working group to provide at the end a standard.
Okay, so these are the tools that are already developed. One more last thing important is the fact that we are trying to have an open source approach and a very open architecture. So all you guys are familiar with that, but maybe less with what we have here. So inside on the left of the slide, you see inside of the research project, we have a reference implementation, which is implementing the architecture using DDS, XML, RPC, the state chart XML, and ED247. This one is available on a GitHub inside Airbus, but accessible to all the research project partners. But we, thanks to Geoffrey Delhomme here and Olivier Fourcade, we have a completely free implementation of ED247 available on the web, which is the ED247 library, and it's on the web GitHub, so the classical github.com. So that's very key, because if you want a standard to achieve its aim, it needs to be used. So at no cost. Also, we are collaborating with other projects, but that's more an internal thing. So the next step we will take is, as I showed at the beginning, we are funded by the French and the German body. And so after the pandemic, we try to restart the funding, and it looks okay. We try to secure also the partners which have been going through difficulty. So the use case is hard to pursue, but now we are looking at a promising demonstration next year. And we look forward to share experience with you guys, okay, for the technical solution we are proposing, because we know we already have a significant amount of partners, but we know we are not alone. Since I worked in the microelectronics industry before, I know it's not even the only domain we should address, and that's why we are here today, to exchange with you and try to see, because the problematic of the simulation bench is very close to the simulation of components using System C or other language. So there are really some parallels that should be drawn, and that should allow us to focus on the real challenges of our industries, instead of too much focusing on the how to do it thing. And the how to do it for us is the bench. And we are trying to make the bench as automated and light as possible to focus on the aircraft function, because that's really our job. Okay, so that's it for me, Mark.
You're a very greedy man, and you've taken 10 minutes more. Martin
Sorry.
Not your fault. Martin is proposing that there's actually a time slot this afternoon that we could potentially meet in. Let's see whether that's possible later. Let's see who's available when we get to the end of this meeting. Let's move quickly on to FMI and FMU, unless anybody's got a very urgent question for Jean or Oliver.
Okay.
Let's go straight on then. Thank you very much.
Hello.
Hello.
Okay. No, I thought we couldn't hear Mark anymore. I'm wondering if.
It's going well.
Okay, you see my screen?
Yes, we do.
Oh,
okay. Okay, so hello everyone. I'm Jean-Marie Gauthier from Summaries Engineering, and I will present you an overview of the FMI standard. Okay, so FMI is an open standard, and FMI stands for Functional Mockup Interfaces. So the main goal of this standard is to integrate together heterogeneous models from several simulation tools to be able to build co-simulation graph, or to exchange simulation model. So the standard is available at the website and in the slides. So the main motivations for this standard is to be able to build and share simulation models between OEM and suppliers, where suppliers may have different simulation tools and simulation languages. So the main solution is to be able to reuse supplier models by importing GLL or binaries. It is a compiled model. Or also to perform cross-simulation using tool coupling. And another main motivation is that with FMI, it is possible to protect the intellectual properties, because an FMU can be seen as a black box model. So you just have access to the interfaces, or the white box models, where you have access also to the source code of the models. So with FMI, there is no proprietary middleware. The API is open. And the main added value is that you can connect an FMU, build from any tools to perform early validation of any kind of design. So at the first, FMI was mainly used in the automotive industry, but now it's spread off a lot of industries. It improves software model and hardware in the loop simulation of physical model from different vendors. And there's been at the beginning 14 automotive use cases to evaluate FMI. So the main idea is to, let's say you have several suppliers, each one is responsible for a subsystem, one for the engine ECU, another for the gearbox ECU, etc. And the integrators is now able to integrate, to receive first the model and to integrate all the models together to perform verification, validation, and using co-simulation. So FMI is the standard, but a model is called an FMU. So FMU is a functional mockup unit. It is basically a zip file which contains binaries that are generated from any kind of tool that is compliant with FMI. And so you can have binaries for Linux, Windows, or any kind of other operating systems. And with these binaries, you have also what is called a model description file, which is an XML file. And it defines inside this XML file all the interfaces and the state variables for the models. So this slide. This slide shows in more detail the model description XML file. So the schema, and so the first part, the top part, are just to define if the FMU is for model exchange or co-simulation. Then you can define some units, some types, etc. And the most important parts of this file is model variables and model structure, where in model variables, you can find what is called scalar variables. It can be of 5 types, so real, integer, boolean, string, and enumeration. And you have also the model structure below, which define what are the outputs, the derivatives, and potentially what are the dependencies between outputs, variables, and inputs for each variables and outputs. So there is a limitation now concerning the types that are available with FMI. Since we have only access to these 5 types, it's quite hard to deal with complex interfaces like arrays or matrices. But I think there is work to manage this in the future version of FMI. So with FMI, you have 2 main approaches, FMI for model exchange and FMI for co-simulation. Note that there is 2 versions also of FMI. So the first one has been released in January 2010, and the second one in 2014. And for those 2 use cases, 2 main approaches, I will enter into details for each of them. But note that in model exchange, you need a solver. When you receive an FMU, you need a solver to execute the model. And for co-simulation, the solver is embedded into the FMU. So you can take it as is and execute it in your own tool, even if your tool does not have any solver inside. So for the capabilities of FMI, basically each tool is able to import, each tool that implements the FMI standard. Basically you can import or export your models into an FMU. With FMI, we can simulate also differential and algebraic equations, and it's also discrete equation with time events, state events, and steps events, like in Modelica or any kind of multiphysical and hybrid simulation tool. It is possible to have big FMU with thousands and hundreds of variables, and FMUs can be connected together to build what is called a co-simulation graph. So now I will enter into detail into FMI for model exchange. So basically a tool that is able to export an FMU for model exchange will compile your models, your Simulink model, for instance, or Modelica model into a binary file. It will also generate this model description.xml, which represents the structure and the interfaces of the FMU. And so this is for the export. And then let's say you have generated, why it's going alone. You have generated an FMU from Modelica. You want to import it into Simulink. So then you have a tool here that is able to import this FMU. And for model exchange here, you need a solver to call each step and to solve at each time step the model which is compiled into the FMU. So simulation, the main goal is to have several simulation tools or several models that are coupled together to perform a full co-simulation. Each FMU is considered as an independent object that owns its proper solver and way to solve itself. But in co-simulation, data are exchanged at specific communication point that is tunable. And so it is quite useful if we want to simulate heterogeneous systems and have a kind of partitioning or parallelization of large systems to simulate. And also in a hardware in the loop simulation where we have components, virtual components as an FMU to be connected to, let's say, a real ECU to simulate or to validate. So for co-simulations, the main idea is the same. The export works the same as FMI for model exchange. It generates a binary file from C code. But this time with the model, the tool is able to generate also the solver, to embed the solver inside the FMU. And if, let's say, you want to import an FMU for co-simulation into a simulation tool, this time the tool needs what is called a master algorithm to synchronize all the FMUs together, because each FMUs communicates its output at specific global time step. So with FMI for co-simulation, we have what is called a master-slave architecture. It considers different capabilities of simulation tools for import and exports of FMU. Also considering the master algorithm, with FMI, the standard for FMI does not specify the master algorithm that need to be developed to co-simulate together several FMUs, neither the communication technology for distributed scenarios or for parallel simulation or distributed simulation, for instance. However, some tools that are compliant with FMI for co-simulation are able to generate master algorithms from the co-simulation graph. It means that if you have a complex co-simulations made of FMU, you will probably need to build your own master algorithm to synchronize all the FMUs together. So there is specific master algorithm for each co-simulation graph when they become complex. Also, there is 2 use cases for cross-simulation with FMI. So you can import an FMU, as I said before, and then you have your master algorithm that can call the FMU at each communication step size. Also, you can connect a tool. So let's say you want to connect several Simulink together with other tools. Then you have a simulation tool that plays the role of the master. And with the FMI wrapper, you are able to connect other simulation tools that are the slaves for this master. So it's the same. The simulation results are the same, but this time it is the simulation tool that is connected and not directly an FMU. Also, there are work and possibilities to perform distributed co-simulations. So let's say you want to have several computers connected together, and each computer is responsible of one part of the system, which is one FMU. So you will have the same master algorithm, and which is responsible to synchronize all other slaves together, so all other computers together. And here the data exchange is handled by a communication layer, which is implemented by a special FMI wrapper. And master and slave use FMI for co-simulation only, which means that it's not possible to have this kind of architecture, distributed architecture, when we use FMI for model exchange. The solver should be embedded in each simulation node. So what you see here are sample codes for each way to use FMI. So for model exchange, you have one model evaluation at each time, and it's able to handle the events and the continuous states and the discrete states of the FMU. But for co-simulation, you only have access to the input and output at each what is called global co-simulation step size, so TC or HC. So at each global step size, you get the output of the FMUs, and you propagate them to the input of the other connected FMUs with the API, FMI, set real, or two step to perform the one step size computation. And then we get the results at the output Y of each FMU. So you can find in the website of FMI a lot of tools that implements these standards. I think the list is not exhaustive, but the list if the tool is open source or free or not, I mean, the kind of platforms, if they implement which version of FMI 1.0 or 2.0 it's implement, and for co-simulation or model exchange. So this is on the internet. Also, FMI is not the only standards for co-simulation. There are other standards that are currently being developed with FMI to be used with FMI in collaboration with FMI. So the first one is SSP, System Structure and Parameterization, which specify the co-simulation graph. So FMI does not specify this, it specifies only the interfaces of one model. With SSP, it's now possible to specify a full architecture of co-simulation made of FMUs with some parameters that can be global or local to one FMU. And so it is possible to have a kind of a matryoshka architecture with several, nodes that are made of several also co-simulation graphs. So you can have big integrated co-simulation architecture, which is kind of standard. And DCP, which is for more for distributed co-simulation, and it specifies more the protocol and the interfaces when we want to, let's say, allocate different simulation nodes to computation system. And it's more focused on real-time extensions to integrate this FMI standard into distributed co-simulation. So I was maybe quite fast, but so as a conclusion, FMI is widely accepted in the computer-aided engineering world. It has been initiated in the ITEA2 Modelizer project, and it has been defined in close collaboration of different tool vendors. There are a lot of individuals that were involved to these standards and for proof of concepts. And it's currently being developed. As I said, FMI 2.0 has been released in 2014, and there is FMI 3.0 that is not now available, I think, but it's I mean the Modelica Association and all the industrial partners are working on it since two years now, I think, 2 or 3 years. And also there are complementary standards. So as I said, SSP and DCP to build a complex and distributed co-simulation architecture. So thank you for your attention. If you have any question.
Thank you very much for keeping it roughly in time. We'll move on unless there are questions. Are there any quick questions for Jean-Marie? So our final presenter is Andy, who is going to give us more of a use case, I suspect, as well as yet another set of standards.
Yep. So trying to share my desktop. So hopefully you can see it now.
Yep, looks good.
Okay, so let's talk a little bit about autonomous driving stuff. So who am I? So I'm Andy, working for Bosch as a technical product manager for autonomous driving. I'm with Bosch for about 23 years, 15 years of experience in embedded software development and trying to bring open source within Bosch forward. So first of all, let's talk a little bit what makes autonomous driving complex. So therefore, the car has to mirror the driver's ability to see, evaluate, and act. Means you have to look around what is going on the car's environment. The next step is you have to be able to pinpoint the location in order to know where exactly you are. For example, are you in Stuttgart in Germany or are you in Stuttgart in the US? It's a big difference as well, knowing on which lane you are driving. Third, based on that information, the car has to interpret, to plan, to decide how and where to move. That means it has to process the data received from the sensors and of course of the cloud. Next step is based on the data, it has to find the best trajectory for the driving task, which will then be executed by its actuators. So open source arrived also in automotive. So I have some examples on that for you with me. So for example, Autonomous Future is open source. The Autoware Foundation open sourced some interfaces and tools. Uber open sourced AVS, an open source standard for autonomous vehicle visualization. Maybe you know also Kala, an open source simulator. Then there is KAMAR. It's a project from the US Department for Transportation dealing with vehicle-to-X communication. LG also open sourced here a simulator for AVs for the ROS and ROS2 framework. Tesla published here open source code for their Model S and Model X. Uber and GM Cruise are making their AV visualization tool open source. Then you have Continental, one of the biggest Bosch competitor, who do some open source stuff. Here it's eCall and enhanced communication abstraction layer. Then Audi are doing the same thing as well. They open source their autonomous driving data set, some machine learning algorithms or libraries, and their so-called functional engineering platform, which they use for model in the loop, software in the loop, hardware in the loop purposes. And this is really interesting because looking a little bit back, open source in automotive was a real no-go, therefore, and it's now really cool that we have here some initiatives, some open source code within the automotive industry. So yeah, as I told you, autonomous driving development is really complex. You need a lot of tools, therefore, and often you choose best-in-class tools, and often they are not designed to work together with other tools from different tool vendors. And to make them work together, you have to build some connectors, and every company is doing that by themselves, and this costs the industry a lot of time and money. And therefore we initiated OpenADX to mitigate these problems and to accelerate then the time to market, share costs and risks, and free up resources to focus then on the real customer needs. By defining an industry-wide accepted AD tool chain with a high interoperability and easy access to establish a base for a reference architecture. And therefore, we found with the Eclipse Foundation, and yeah, please, I know some of you are open source guys, but to be sure, Eclipse Foundation and Eclipse IDE are two different things. So it doesn't mean that we are relying directly on the Eclipse IDE. So it's more the umbrella for us, it's the Eclipse Foundation. And yeah, they host us. And the current members we have there is Microsoft, it's Bosch, it's Denso as a further automotive player. We have AdLink, AVL with there. So we heard also in the former talks something about co-simulation. AVL, for example, they have a co-simulation framework called Model Connect, and they are currently open sourcing parts of them in a project called Eclipse OpenMCX. We have Red Hat, Iteration from Turkey, Eclipse Source, Itemis, Siemens, JSIM, the Science and Computing AG, a part of the Atos company, the University of Applied Sciences and Arts in Dortmund. We have the Open Robotics Foundation in there and the Autoware Foundation. So here you can see a little bit on our approach we have. So we want to integrate a range of existing products in our development suite. So you can see here with the blue bubbles, with the blueprint here, our blueprint, and knowing it's not 100% complete, but a good starting point for go into the discussions. So the color code, so I try to activate here the laser pointer here, will show you that you have a lot of vendors, many specialized tools, and from different companies. Our goal is not to define the one and only tool chain. No, we are trying more to focus on the tool interfaces to make them standardized, to look on the data flow and the data models, to make here the tools within that exchangeable. So as mentioned, we do not want to define the one and only tool chain, because every company, so you can look here in the horizontally line, has invested in their tool chain, and they won't exchange here too fast, too many tools, because they invested in that by buying licenses and training of the employees. So to make here a complex toolchain more accessible for the enterprise users, here you can see a little bit of our approach. You can see here the toolchain. We think it should be in the cloud because then you have, or you can guarantee the easy access. You have a maintained and hosted toolchain. Therefore, what do you want to do with a cool toolchain? You want to make here some cool products. And here's an example of a software stack with perception, location, think, act, our automotive middleware, where we have Eclipse Isorix, one further project in there. And we have also here some open operating system projects like Zephyr, which can be here below that. And you know also that there are some open hardware initiatives like RISC-V, so that you can at the end, or I'm dreaming here of a software development kit based on open technologies. But with the marketplace, you can also imagine that we can use here commercial products as well as open products in there, so that you can build here your own tool chain and build here your base software stack where you can start with building the stuff you wanted to use. And to be honest, the toolchain is not only located to autonomous driving, so you can use it also for other things. To make here at the end the way between the developer and the vehicle as short as possible, so with over-the-air possibilities, you can easily download here the software into the car, bring back here measurement data for pre-processing, for post-processing, for simulation aspects, resimulation, recomputing, and so on. So, and here you can see here the interfaces we have currently with other Eclipse projects, for example, the OpenMDM, handling of measurement data, OpenGenesis, verifiable and understandable AI, Open Mobility, which is hosting also Mosaic, Eclipse Mosaic. So Rashid mentioned it in his SMP talk. They have also Sumo for urban traffic simulation. So they have a conference in parallel currently. Then OpenPath dealing with some simulation aspects coming from accident research, but it's not only related to accident research, their simulator. Then there are also some public funded projects out there, for example, especially for simulation purposes. Then there are also some further projects for the FMI, for the automotive stuff like Eclipse Cuxa. They have an IDE, App4MC with an exchange platform for timing performance simulation, and the successful project Panorama for design efficiency. Yeah, we heard about it, FMI standard. So Bosch is also part of Modelica, open hardware, and of course, a lot of more things out there. So just coming to our current projects we have Eclipse Chloe. It's a closed simulation environment, but with not a real simulation engine there. So it's more an abstraction layer or a connector to connect here the simulation engine with the AD software or with the software you want to test. Chloe provides you here a user interface so that you can, for example, activate here some functionalities, adjust some simulation parameters, so and to have a look what is going on there. So just some words on Eclipse Isorix. Isorix is a true copy, a true zero copy shared memory approach for inter-process communication. Means we do not copy messages within some tasks. We handle references from a mem pool, therefore. So yeah, what we are currently doing is to build here a program plan. So what we want to do next year, we are currently building a demonstrator. Therefore, we have here, you can see it here as well, Eclipse Mosaic, we have Sumo in there, trying to do based on a platooning use case, a co-simulation demonstrator. Then we are starting also to build here a development workplace where we want to bring in here as many parts of the blueprint as I showed you. And what else? So it's also up to you. Let us know. And just to sum up, yeah, open source, it's also gaining traction in the automotive in the automotive industry. And yes, it's there, and it helps us, and yeah. So here's some links for that, and yeah, thank you. Yet now we came to the questions, so I guess we do not have too much time for that, so sorry for that. And yeah, Mark, I get it to you. Thanks.
Brilliant that you've managed to bring yours in quickly so that we have a few minutes. I think we have 7 minutes left for a few questions. One question is whether or not people are free to continue the discussion, because I think it could be quite interesting later on today. There's a potential time slot between 4 and 5 o'clock today. In the chat session, if you would like to just say whether you would or would not be available for that, that would be very helpful. And if the presenters, if I can just go quickly through the presenters, I already have back from Jean-Marie, Jean Castres and Olivier. Would you be available for that time slot?
At 5?
4 to 5.
Okay, let me look up.
And also, Andy, would you be available for that?
I'm very sorry. I have a meeting in parallel, so it's especially for OpenADX. We have steering committee meeting today, and as I'm the chair of OpenADX, I cannot skip that.
Okay.
So sorry for that, but you can of course. I will post my email address into the chat, and you can of course contact me here via email.
So are there questions particularly for Andy on OpenADX? I think it's kind of interesting that you're looking at a higher level, as it were, of integration between different standards. And one question I had was whether or not some of the other standards we've talked about should be connected in to OpenADX. But are there other people with questions for Andy? Do you want to answer my question then, Andy?
Yes.
You already have MIFMU, but how do you feel about some of these more domain-specific simulation environments? Indeed, not so domain-specific, the Accelera environments, for instance, would they work within the standard?
Yes, from my point of view, yes, and as you mentioned, there are a lot of standards, and it's also kind of how to approach to the different standards. So we are currently looking more on the FMI standard, knowing that there are more out there, and yeah, trying to bring them together for our purposes. And as I mentioned, yes, we are coming from autonomous driving, but the tool chain, it's more general. So, and if our approaches works, then you can build your tool chain for every kind of project you want to use, and therefore you need then also some other different standards, especially for simulation. If this answers your question.
Yeah, it kind of does. I mean, I think one of the issues that we have, and I'd like everybody's feedback on this in the last few minutes that we have, we've kind of, apart from you, Andy, we've heard effectively 4 people saying, me too, I've done pretty much the same thing. I mean, with different focuses, with in different domains, with different specialities. But I mean, what I find interesting about OpenADX is that you've recognized the problem and you've kind of gone, right, well, we need to do something to combine all of this together, at least within the domain of automotive. And I guess the question that was behind putting this workshop together was, should the same be done, but without a particular domain in mind? Should it just be that we can coordinate between these different standards?
Yeah.
And I think you kind of answer the question very succinctly from the automotive perspective. But then the next question is, to what degree the various different standard bodies want to work together and how they could work together. I mean, for instance, FMI, there's a large community of people who are using FMI now. It's not obvious how you would then, I mean, I don't think you can change that, right? that people are going to use it.
Yeah.
So the question then is, how do you, what is the best approach to integrate things like TLM2 and SMP2, and what can be gained from Vistus as a transport mechanism?
That's a good question. I guess we have to start here also with a separate workshop to bring things together. So as far as I understand, so some of the talks mentioned also DDS, and within Eclipse we have also some implementation of DDS. I guess we have to do also a kind of research. What is there? What can be used for which domain, and how can we bring that really together? I guess it's not really necessary, for example, spoken for DDS, to have thousands of DDS implementations. I know that there are not thousands out there, but there are a lot of them out there, and so we have to think or have a look on what is really needed from every domain, and what can be then the solution. I guess DDS, it's a standard, and we have our open source project ISORIX in there, or we're currently on the way to bring that in there, so that we have here one further based in the open source direction. And as far as I have it right in mind, a lot of the talks was also in this direction, to bring that open source, or having some things open source. And standards, of course, they should be open, because then everyone can adopt it, can use what they need for that, and maybe can also extend these standards to the specific needs, I guess.
It seems to me that the result of our discussions today, I think we now have a better understanding, perhaps, than we did before, about the wealth of standards out there and the overlap between them. I also get the impression that actually all of us are relatively interested in getting those standards to combine together in some way. And I think, Andy, you gave a particular good kind of driving motivation for that. I guess the big question is, okay, so what is the next step? 4 o'clock to 5 o'clock is not looking great for an awful lot of people. So let's abandon that for the time being. By all means, we can use the virtual environment here that DVCon is providing to meet and chat. But what I suggest, I mean, it's what you just said, Andy. We really do need more workshops, more ways in which we can meet and discuss and work out technically and physically, as it were, on the ground, what can be done to make the standards communicate with each other.
Yeah.
I will potentially and hopefully propose follow-up meetings of this group. Those who are, I mean, the 5 presenters and myself, or 6, I will obviously directly get in touch with. But it would also be good if you can be in touch with me, those of you who are listening to this workshop. If you can get directly in touch with me if you're interested in being kept in touch with the workshop, that would be really, really helpful. And then I can, if there are follow-up workshops, which hopefully there will be, then we can organise that. I mean, obviously, one option will be to have a follow-up on this workshop next year, hopefully face-to-face.
Yeah, so what we can do, Mark, from a DVCon Europe or Accelera point of view, is that we can somehow currently take the lead to start this alignment, and and then make sure we have a discussion forum started, and let's say the setup of a Teams or WebEx session later this year or early next year should be feasible, right?
Yeah, that sounds like a really good idea, Martin. Thank you very much for offering Accelera's services in that respect.
Mark?
Yes, John.
For this afternoon, it doesn't look very good for me on my end, and neither for Olivier, but we'll welcome some wrap-up meeting next year. And I also wanted to mention to Jean-Marie that we are connecting to FMU, FMI, and if he has a chance, I had a question for him if the concept of FMU model distribution is similar to the one we are presenting in Vistas with ECD, CIC. And if he's interested in answering that question, we can talk offline.
Yes, no problem.
Okay.
Yeah, I think, I mean, I was extremely interested to see the FMI, FMU way of doing things and how it overlaps so much with the other ways in which people are organizing model distribution.
Yeah, but the thing is, as you realize, Mark, not all of our equipment provider are using FMI, FMU. So, and we have legacy models that we cannot force them to rewrite.
Sure, and I guess one of the open questions in my mind is, moving forward from here, is the right approach a kind of wrapping gasket approach where, you know, there exists a gasket which takes a model that is in SMP2 and connects it to TLM2 or FMI or whatever, or is a better approach to look at TLM2, SMP2 and try to in some way merge the technologies? And as I say, I think when it comes to FMI, that's kind of an immovable beast already. But maybe some of the other standards are more amenable to change. But I think that's a real open discussion.
Yep.
Sounds like an agenda item for a next meeting.
Thank you very much indeed, everybody, for taking part. It's been a pleasure to hear, particularly from the presenters. Hopefully it's been useful, and I think we're completely out of time. Thanks very much, everybody.
Thank you, Mark, for organizing this.
Yeah, thanks, Mark.
Thank you.
Thanks, Mark.
Thank you.
Bye-bye.
Bye.
Bye-bye.
Bye bye.